Ever been stuck in traffic and just, wished you could see everything from above? Find that magic shortcut.
Oh, yeah, definitely. Or wondered why all the coffee shops seem to bunch up together in one area.
Exactly. That kind of spatial thinking, understanding where things are and why. Well, that's basically what we're digging into today.
That's right. We're looking at Geographic Information Systems, GIS, and what a GIS analyst actually does. It's all about making data smarter by knowing where it belongs on a map.
Totally. And it's way more than just making, pretty maps. Those are useful too. GIS is like this framework for pulling together all sorts of data.
Spreadsheets, satellite photos, you name it.
Right, and connecting it all to actual locations. So you can see patterns, you can see relationships, you layer it all together. Maps, 3D scenes, the works. And for you, the learner, our mission today is pretty simple. Give you a clear view of GIS where it pops up sometimes in surprising places and what skills you'd need if you were working in this field. We're aiming for those aha moments without getting bogged down in jargon.
Yeah, we want to make it accessible. And we're using insights from GIS Analyst interview questions as a kind of guide. It gives us a good structure.
Sounds good. So let's jump in. What is GIS, fundamentally? And where does it actually get used?
Okay, so at its core, GIS is about data that has that geographic piece. It's tied to a place on Earth. It works on the idea that almost everything happens somewhere.
And that somewhere is often really important for understanding the why.
Exactly, for analysis, for making decisions. And you'd be surprised how many fields rely on it. Want to walk through some examples, maybe some that hit close to home for people?
Sure. Like, think about cities, how they grow, how they change.
Urban planning, right?
Yeah. Planners use GIS to decide where new roads go, or parks, or housing. They can look at current land use, map it all out, and then project future needs based on, say, population growth.
And not just how many people, but where they're moving to, right? So you can target development.
Precisely. It helps manage zoning, infrastructure, makes the whole process much more data-driven.
Okay, that's a big one. What about the natural environment?
Oh, hugely important there, too. Environmental conservation.
Right. Monitoring resources like forests or water quality, assessing the impact of, I don't know, a new development.
Planning where to focus conservation efforts. You can map things like deforestation or track wildlife movements or see how pollution is spreading geographically.
Seeing it visually makes a big difference in understanding the scale of the problem.
Definitely. Okay, here's one people might not immediately think of. Farming, agriculture.
Yeah, absolutely. GIS in agriculture. It's about precision. Farmers can analyze crop yields against soil types, maybe irrigation patterns, even track pests, all mapped across their fields.
So they can be really specific with resources.
Exactly. Use fertilizer or water only where it's needed most. Target interventions, boost efficiency, boost yields. It's smart farming.
Precision agriculture, yeah. Makes sense. Okay, what about just getting from A to B?
Transportation and logistics. Heavily reliant on GIS. Think delivery companies planning the most efficient routes.
Or public transport planning.
Yep. Or even just your phone's map app getting you home the fastest way. That's all GIS network analysis working behind the scenes, finding the best path.
Okay, that makes total sense. And it's even in healthcare, public health.
Oh, for sure. Tracking how diseases spread, especially during outbreaks.
Yeah.
Identifying vulnerable populations based on location. Managing resources, like where to put clinics or distribute vaccines.
That became so visible recently, didn't it?
It really did. Mapping cases helps find patterns, understand transmission routes.
And in emergencies, disaster response.
Crucial. Absolute crucial. Planning evacuation routes, assessing damage after a flood or fire by overlaying hazard maps with buildings and population data.
So you know where the impact is worst.
Right. And coordinating relief efforts. Getting help where it's needed most, fast. Plus, risk analysis predicting where future disasters might hit hardest.
Wow, okay. And even something like buying a house.
Real estate, definitely.
Yeah.
Market analysis. Understand property values based on location, proximity to schools, parks, transit.
Demographic data for the neighborhood.
Exactly. Mapping all that helps agents and buyers make much more informed decisions.
It really sounds like a GIS analyst needs a pretty broad skill set, then it's not just map making.
Not at all. It's this blend, technical chops, definitely. But also strong problem solving. How do you use location data to answer this specific question? And communication skills are key too.
Communicating complex stuff, simply.
Yeah, explaining spatial insights to people who aren't GIS experts.
Okay, let's dig into those technical skills. What specific software or tools are we talking about?
Well, GIS software proficiency is fundamental. The big name, commercially, is ArcGIS. It's really a suite of tools.
I've heard of ArcMap.
ArcMap is the classic desktop tool, yeah. There's also our catalog for managing data, the newer ArcGIS Pro and ArcGIS Online for web stuff. It's pretty comprehensive. Analysis, automation, what we call geoprocessing, making shareable web maps.
Okay, so ArcGIS is a major one. Are there alternatives?
Oh, yeah. Open source is huge in GIS, too. QGIS is probably the most well-known.
QG?
Yeah, it's really powerful, free, has a massive community developing plugins for extra functions. You can script with it, too. Very flexible.
So not just one tool to rule them all.
No, definitely not. And knowing related tools helps. Like, Iridescimagine Imagine is often used for remote sensing analyzing satellite or aerial imagery.
Okay.
And things like GeoServer are important for publishing maps and data as web services, making them accessible online.
Right, so others can use your maps in their own applications. And it's not just the visual software, is it? Databases play a role.
Huge role. Spatial database management is critical. PostgreSQL, with the PostGIS extension, is super popular.
PostGIS.
Yeah, it basically teaches a standard database how to understand and work with geographic data points, lines, polygons. Makes storing and querying location data really efficient.
Okay, so you need the software for the analysis and visuals, but also the database skills to manage the underlying information. Let's make this more tangible. Can you walk us through an example project? How would an analyst tackle something?
Okay, let's go back to that emergency response idea. Optimizing routes in a city.
Right.
So the analyst starts by gathering data, road networks, obviously, but also traffic patterns. Average speeds at different times of day, historical response times maybe.
Layering it all together. Got it.
Then, using network analysis tools, probably in ArcGIS or QGIS, they start modeling scenarios. How long does it take to get from fire station A to incident B under typical Tuesday afternoon traffic? What if this road is closed?
Like running virtual drills.
Kind of, yeah. And this is where collaboration is key. Talking to the emergency services folks, what are their constraints? What routes do they currently use? What are the priorities?
Makes sense. You need their input.
Absolutely. The goal is finding routes that consistently cut down travel time.
And what kind of impact could that have?
Well, in the example we look at, implementing these optimized routes, maybe through a dynamic tool dispatchers use, led to a 15% reduction in average response times.
15%? That's huge in an emergency.
It can literally be life-saving. It shows how GIS isn't just theoretical. It solves real problems with measurable outcomes. You'd use techniques like finding bottlenecks, shortest path analysis, fastest path.
Okay, that's powerful, but it all hinges on the data being good, right?
Right.
How do analysts ensure data quality, accuracy, reliability?
Oh, data quality is everything. It's paramount. Several key steps.
Yeah.
First, data source verification. Where did this data come from? Is it trustworthy?
Step 1, check the source. Makes sense.
Then there, data validation and QA/QC, quality assurance, quality control. Running checks within the software.
Like what kind of checks?
Topology checks are a big one, making sure lines connect properly, polygons close, no weird overlaps or gaps. Imagine roads that don't quite meet at an intersection. Topology checks find that.
Okay. Fixing the geometry.
Right. And attribute accuracy checks. Is the information attached to the map features correct? Is the road name right? Is the population number accurate?
Got it. Geometry and the info behind it. What else?
Regular updates. Data gets old fast. New roads, new buildings. Need to keep it current. And metadata.
Metadata.
Yeah, the data about the data, like its ingredients list, where it came from, how accurate it's supposed to be, when it was collected, how it was processed. Crucial for anyone else using it.
So people know what they're working with.
Exactly. And finally, cross-verification, checking against other independent sources whenever you can, just to confirm things look right.
It sounds like a lot of careful checking, but I guess it has to be done.
Absolutely.
Yeah.
Garbage in, garbage out, right? You need reliable data for reliable results.
Okay, so assuming the data is good, what are some common ways analysts actually analyze it? Those spatial analysis techniques you mentioned.
There's a whole toolbox. Buffer analysis is a common one.
Buffer.
Yeah, creating a zone around a feature, like draw a circle 500 meters around a factory to see what homes fall within that potential impact zone. It's about proximity.
Okay, zones of influence. What else?
Overlay analysis. This is really powerful. You stack different layers of information on top of each other to create new insights.
Like combining maps.
Exactly. Maybe overlay a map of wildlife habitats with a map of proposed logging areas to see where the conflicts are. Or identify prime conservation spots.
Stacking layers to find new meaning. Cool. And network analysis we touched on?
Yeah, fundamental for anything involving movement. Finding the best routes, calculating service areas like how far can you get from a hospital in 10 minutes. Analyzing connectivity. Huge for transport, logistics, utilities.
Okay. What if you only have data at specific points, like weather stations, but you want a map of the whole area?
Ah, that's spatial interpolation.
Yeah.
Using the known values at measured points to estimate the values at places you didn't measure.
So like educated guessing based on nearby points.
A very smart kind of guessing, yeah. It lets you create continuous surfaces like that temperature map from scattered weather stations. Fills in the blanks.
Filling in the blanks, got it. And hotspot analysis, I've heard that term.
Right, that helps you find statistically significant clusters. Where are values unusually high or low compared to what you'd expect randomly?
So not just high values, but clustered high values.
Exactly. Useful for finding crime hotspots, disease clusters, areas with high pollution levels. It helps target interventions or further investigation. You might find a link between, say, pollution sources and health issues this way.
Okay, so these techniques really unlock the stories hidden in the spatial data. Now, this tech changes fast, right? How do GIS pros stay up to date?
Constant learning is non-negotiable in GIS. It evolves so quickly. Reading is key GIS journals, magazines like GIS Professional or ArcUser. They cover new research, software updates, case studies.
Keeping up with the literature, what about interacting with other pros?
Super important. Online communities are great for that. GIS Stack Exchange for Q&A. Reddit has a big GIS community. Esri's own community platform, GNet.
Places to ask questions, share solutions.
Yeah, troubleshoot problems, learn from others' experiences. You can pick up so much just browsing those forums. Find a fix for a coding bug, discover a new tool.
That peer learning aspect and more formal training.
Definitely. Workshops, webinars, big conferences like the Esri User Conference. You get hands-on training, hear about the latest stuff directly from the source.
Networking opportunities too, I bet.
Huge. And online courses, Coursera, Udemy, Esri's own training portal offer deep dives into specific skills or software.
So reading, online communities, formal training, courses.
And networking, yeah.
Yeah.
LinkedIn, local GIS user groups. Just talking to people in the field can spark ideas, lead to collaborations.
It really sounds like being a lifelong learner is baked into the job. Now, back to databases for a sec. Why are database skills, and specifically SQL, so crucial?
Well, GIS deals with data, often lots of data. So knowing how to organize, store, and manage that spatial data efficiently in a database is fundamental.
Designing the database structure?
Yeah, using systems like PostgreSQL with PostGIS, or maybe SQL Server. PostGIS is great because it adds those geographic capabilities, understanding points, lines, polygons right into the database.
And SQL, what does that do?
SQL structured query language is how you talk to the database. It's the language you use to ask questions, to pull out specific data, to manipulate it, even perform analysis within the database.
So you could use SQL to find, I don't know, all the schools within a certain city district.
Exactly. Or calculate the total length of roads maintained by a specific department. Or find customers who live more than 10 miles from the nearest store. You ask the database using SQL.
Got it. It's the query language. And performance matters with big data.
Hugely. So understanding things like database indexing is important. Indexes are like a book's index. They help the database find data much, much faster, especially on large tables.
Speeds things up.
Right. And these skills also help integrate GIS data with other systems in an organization, making sure everyone's working off the same page. Database maintenance, backups, updates, that's part of it too.
Okay, so database management and SQL are really foundational. Now, you've got all this data, you've done the analysis. How do you explain it to someone who doesn't speak GIS? That communication piece.
Ah, yes. Super critical skill. Several techniques. Simple visuals are key. Clear, intuitive maps and charts. Don't clutter them. Highlight the main message. Focus on the what's and why, not necessarily the complex how.
Keep it clean and focused.
Exactly. And storytelling helps. Weave a narrative around the data, connect it to things the audience cares about. Make it relatable. Instead of just stats on traffic congestion, show a map of the worst bottlenecks and talk about the impact on commuters' daily lives.
Make it human. What about letting people explore themselves?
Interactive tools are great for that. Web maps, dashboards where users can click around, zoom in, explore the data that interests them.
Giving them some control.
Yeah. And when presenting formally, use plain language. Avoid jargon. Emphasize the implications of the so what for the decision makers. What action should be taken based on these findings?
Focus on the takeaways.
Right. And sometimes offering workshops or quick training sessions for stakeholders helps them understand and use the GIS products better.
It's about bridging that technical gap. Okay, let's get really practical. If you had to make a map from scratch, what are the steps, start to finish?
Okay, map creation. It's a process. Step 1, define the objective. Why are you making this map? Who's it for? What question should it answer? Clarity upfront is vital.
Know your goal, then.
Data collection. Gather all the spatial data, the stuff with locations, and any related attribute info you need. Make sure it's from credible sources.
Get your ingredients.
Then data preparation. This is huge. Cleaning the data, fixing errors, making sure formats are consistent, getting it ready for the software.
Prep work, okay.
Next, set up the project in your GIS software. Define the map's geographic extent. And crucially, choose the right coordinate system and map projection.
Projections again. Why is that so important here?
Because the projection determines how the 3D Earth gets flattened onto your 2D map. The wrong choice can distort distances, areas, shapes. You need the right one for your specific region and purpose to ensure accuracy.
Got it. Accuracy depends on the right projection. Then what?
Analysis. Do the spatial analysis needed to answer the question defined in step 1. Extract the key information.
Okay, do the number crunching.
Then map design. This is where you lay out the map elements, the data layers, title, legend explaining symbols, scale bar, north arrow. Think about composition.
Making it look like a proper map.
And styling. Using good cartographic principles. Choosing colors, symbols, labels that make the map clear, readable, and visually appealing.
The art and science of map making?
Exactly. After a draft, review and revise. Check everything. Accuracy, clarity, does it meet the objective? Get feedback maybe.
Quality control for the map itself.
Finally, export and share. Save it in the right format, PDF, image file, or active web map, and get it to your audience. Always keep that audience and purpose in mind throughout.
Sounds like a thorough, iterative process. Okay, another term, geocoding. What's that?
Geocoding is pretty straightforward conceptually. It's turning text-based addresses or place names into geographic coordinates, latitude and longitude.
So turning 123 Main Street into a point on the map.
Exactly. It lets you plot location-based lists onto a map.
Okay, give me an example. When would an analyst use that?
Sure. Say a retail company has a big list of customer addresses in a spreadsheet.
Right.
An analyst can geocode that entire list, turning each address into a point on a map. Then they can overlay that with their store locations.
So they can see where customers are clustered.
Precisely. See where there are lots of customers, but maybe no nearby store. It helps identify underserved areas, potential spots for expansion. Turns a simple list into spatial business intelligence.
Taking addresses and making them strategic. Cool. Now, data types in GIS. You hear raster and vector a lot. What's the core difference?
Okay, fundamental concept. Raster data uses a grid of cells, or pixels. Think of it like a digital photo. Each pixel has a value representing something at that location.
Like the color in a photo.
Or elevation, or temperature, or rainfall amount. It's great for representing continuous data stuff that varies smoothly across space, like satellite imagery. The detail depends on the pixel size, smaller pixels, higher resolution.
Okay, grid of values. What's vector then?
Vector data uses points, lines, and polygons, geometric shapes to represent discrete features, things with distinct boundaries.
So points for?
Trees, wells, specific buildings, lines for roads, rivers, power lines, polygons for lakes, city boundaries, land parcels.
Shapes defining distinct objects.
Exactly. Vector is usually very precise about where boundaries are. It's good for things you can clearly point to or trace.
So raster for continuous surfaces, vector for discrete features. Is one better?
Neither is inherently better. They're suited for different things. Raster excels at surface analysis, imagery. Vector is great for network analysis, boundary definition. Often, you use both in the same project. The choice depends on the data and what you need to do with it.
Use the right tool for the job. Got it. Now, GIS projects often involve teams, right? Can you give an example of how that collaboration works?
Yeah, absolutely. Imagine a project mapping land. Use changes in a growing city. You'd likely have a team.
Different specialist.
Right. Maybe one person focuses on data prep, taking satellite images, old aerial photos, property records from the city, cleaning them up, making sure they're in the same format, same coordinate system, getting the raw materials ready.
Okay, the data wrangler.
Then someone else might do the core analysis, using image classification techniques on the satellite data to identify forests, farms, urban areas, combining that with the property data.
The analyst.
Then you might have a cartographer, someone who really knows map design, taking those analysis results and creating clear, effective maps for reports or presentations.
The map maker.
And maybe you coordinate with a field team, people who actually go out to specific spots.
Ground truthing.
Exactly.
Yeah.
To check if the classification done from the satellite image is actually correct on the ground, verifying the results.
So different roles feeding into the final product. What challenges pop up in teamwork like that?
Data inconsistencies are a classic one. Maybe the satellite image resolution doesn't quite match the property lines perfectly.
Things don't line up exactly.
Right, so you need clear protocols. How do we handle these mismatches? Which source do we trust more in certain situations? Good communication is vital. Everyone needs to be on the same page about data quality standards and methods.
Standards in communication. Sounds familiar. Now, what about huge data sets? Terabytes of data. How do analysts handle that without their computers grinding to a halt?
Yeah, big data is common in GIS. Several strategies. Indexing is key. Spatial indexes help the software find the data it needs way faster without scanning everything.
Like the index in a book.
Exactly. Data partitioning helps too. Breaking a massive data set into smaller, manageable tiles or chunks. Process them one by one or in parallel.
Divide and conquer.
Using efficient file formats helps too. Formats like GeoPackage are designed for performance with large data sets. Even well-indexed shapefiles can work.
Choosing the right container for the data.
Right, and sheer processing power matters. Using powerful software, maybe cloud computing resources, parallel processing if available. Also, optimizing your analysis scripts if you're coding, say, in Python, with libraries like GDAL or ArcPy.
Rating efficient code.
And data cleaning up front. Removing redundant or unnecessary data before you even start the heavy analysis can make a big difference.
So smart data structures, efficient formats, processing power, and clean data.
Got it. Okay, let's say an analyst gets a new data set. What's the systematic process for doing spatial analysis on it?
Right, the analysis workflow usually follows logical steps. First, again, define objectives. What questions are you trying to answer with this data?
Always start with the why.
Always. Then, data acquisition, get the data. Then, really crucial, data examination and cleaning. Look for errors, outliers, missing values. Understand its limitations, clean it up.
Inspect and clean.
If you're using multiple data sets, data integration is next. Make sure they align spatially, same coordinate system. Make sure attribute fields match up if you need to join them.
Get everything lined up.
Then, often, you do exploratory spatial data analysis, ESDA. Make some basic maps, calculate summary stats, get a feel for the data, see if any obvious patterns jump out.
Just exploring it visually first. Yeah. Based on the objectives in that initial exploration, you select and implement the actual analysis methods. Buffering, overlay, hotspot analysis, whatever fits the question.
Run the main analysis.
Then interpret the results. What do they actually mean in the context of your question? This takes critical thinking.
Making sense of the output.
Validation is important too. Can you check your results against other data? Or use statistical methods to confirm significance.
Double-checking the findings.
And finally, documentation and reporting. Record everything. Data sources, methods used, assumptions made, and present the results clearly.
Document the whole journey. It sounds very methodical.
It has to be, for reliable, repeatable results.
Okay, but things go wrong sometimes, right? Errors creep in. How do analysts troubleshoot?
Troubleshooting.
Yeah.
Yeah, part of the job. Need a methodical approach. First, identify the error. What exactly is going wrong? Can you replicate it consistently?
Pinpoint the problem.
Then, check the input data. Seriously, data issues are often the culprit. Is it clean? Is it in the right format? Correct coordinate system.
Rule out data problems first.
Then review your methodology.
Yeah.
Did you perform the steps correctly? In the right sequence? Did you misunderstand a tool setting?
Check your own work.
Consult documentation, the software help files, online forums. Someone else has probably hit this error before.
Learn from others.
Try incremental testing. If it's a multi-step process, test each step individually to isolate where the failure is happening.
Break it down.
If you're still stuck, ask for help. Colleagues, online communities, a fresh pair of eyes can work wonders.
Don't be afraid to ask.
And once you do fix it, document the solution for yourself and others. Saves time next time it happens.
Learn from the fix. Okay, sounds like a good process. Now, GIS analysts often juggle multiple projects. How do they manage their time effectively?
Time management is key. Prioritization is huge. Which project or task is most urgent? Which has the biggest impact if delayed?
Urgency and impact.
Using task lists, scheduling tools, project management software, or even just a shared calendar helps keep track of deadlines and progress.
Stay organized.
Time blocking can be effective. Dedicating specific chunks of time to specific projects minimizes switching costs, helps focus,
Focused work blocks.
and regular reviews. Check in on progress across all projects. Adjust priorities as needed. Communicate with stakeholders if deadlines might slip.
Constant adjustment and communication. Seems like solid project management skills are needed.
Definitely helps.
Now, coordinate systems and projections. We keep coming back to them. Can you really emphasize why they are so fundamentally critical in GIS?
Okay, let's nail this down. They are the absolute foundation for spatial accuracy. They define how locations on the curved Earth are measured and represented on a flat map or screen.
The link between the globe and the map.
Precisely. If you use the wrong system or projection, or if different data sets you're trying to combine use different systems, well, things won't line up.
Was spatially misaligned.
Exactly. Your measurements, distance, area, direction will be wrong. Your analysis will be flawed. Decisions based on that analysis could be way off.
Serious consequences.
Yeah. Proper coordinate systems and projections ensure data integration works. You can overlay roads on satellite images, property lines on zoning maps, and know they match reality because they share the same spatial framework. It's non-negotiable for accurate GIS.
Okay, accuracy, alignment, analysis, integrity. Got it. And there are different types of projections, right? Each preserving something different.
Yes, exactly. No flat map can perfectly represent the curved Earth in all aspects. Projections always involve trade-offs, distortions.
So you choose based on what's most important.
Right. Some projections preserve shape over small areas like the Mercator. Good for navigation, but wildly distorts areas near the poles.
Greenland looks huge on a Mercator map.
Exactly. Other projections, called equal area projections, preserve area accurately. Vital if you're calculating, say, the size of a forest reserve or comparing land masses.
Like conic or certain azimuthal projections?
Conic projections are often good for mid-latitude areas, balancing shape and area reasonably well. Azimuthal projections preserve direction from a central point, useful for radio signals or seismic waves. Some preserve distance along certain lines. You pick the projection whose preserved property matters most for your analysis, while being aware of the distortions it introduces elsewhere.
So knowing the projection's strengths and weaknesses is key. Okay, what about prioritizing when deadlines are super tight? How does an analyst decide what to tackle first?
Tight deadlines. Yeah, that happens. Prioritization gets intense. You look at impact. Which tasks are absolutely essential for the project's core goal? Dependency are other critical tasks waiting on this one to be finished. And effort, how long will this actually take?
Impact, dependency, effort.
Right. High-impact tasks or tasks that unblock others usually come first. Maybe tackle some quick wins if they have high priority, build momentum.
Makes sense.
Clear communication with the team and stakeholders is vital here too. If priorities shift, everyone needs to know. Project management tools help track those urgent tasks.
Keep everyone in the loop. Now, challenges. Can you think of a really significant challenge GIS projects sometimes face and how it's typically overcome?
A classic major challenge is integrating data from different sources that use incompatible coordinate systems. We just talked about why that's bad.
Right. Things won't line up.
It can halt a project if not handled right. The solution is methodical. First, identify all the coordinate systems being used in your input data. Review the metadata carefully.
Figure out what you've got.
Then, choose a single, appropriate target coordinate system for the entire project, one that suits the geographic area and the analysis goals.
Standardize on one system.
Then, systematically reproject all the datasets into that target system using GIS tools. This transforms the coordinates.
The transformation step.
But critically, you then need to validate. Check carefully that the data now aligns correctly. Overlay key features. Look for shifts or distortions introduced by the reprojection.
Verify the fix.
And finally, document everything meticulously. What were the original systems? What's the target system? What reprojection method was used? What validation checks were done? Essential for transparency and future reference.
A careful, documented standardization process. Okay. Now, GIS isn't always just about using existing digital data. How does field data collection fit in? Getting data from the real world.
Field data is often crucial. It starts with preparation. Designing data collection forms what info needs to be gathered, creating base maps for the field crews so they know where to go.
Planning the field campaign.
Then using technology. GPS devices for accurate locations. Mobile GIS apps like Collector for ArcGIS or QField running on tablets or smartphones. Field crews can enter data directly into digital forms linked to map locations.
Capturing data digitally on site.
Yeah, and often that data can be synced back to the main GIS database almost in real time, so people back in the office can see updates quickly.
Live updates from the field.
But quality control is vital. You need processes to check the incoming field data, validate it, Clean up any errors, make sure it's accurate before fully integrating it into the project datasets. Might involve comparing it to aerial photos or doing spot checks.
Verify the field data, too. Okay. And presenting findings. We talked about simplifying, but what about preparing specifically for high-level decision makers, non-technical bosses or clients?
Yeah, that requires extra focus. Know your audience is rule number one. What are their main concerns? What level of detail do they need? What decisions hinge on this information?
Tailor it to their needs.
Absolutely. Focus relentlessly on the key findings and their implications. What's the bottom line? Use strong visuals, clear, compelling maps, simple charts. Avoid jargon completely.
Keep it high-level and visual.
Rehearse. Practice explaining it concisely. Anticipate their questions. Be ready to back up your main points with data, but don't drown them in details unless they ask. Frame it in terms of objectives, risks, opportunities, or return on investment, whatever resonates with them.
Speak their language. Focus on the so whats.
Exactly. Make it easy for them to grasp the core message and make an informed decision.
Okay, taking a broader view again. Environmental conservation and urban planning. How significant is GIS's role there?
Hugely significant. Indispensable, really. GIS lets you integrate so many different types of data relevant to these fields: imagery, sensor data, demographics, infrastructure, ecological surveys.
Bringing it all together.
Right, which gives a holistic view. Then the analysis tools let you model scenarios. What's the impact of this proposed highway on wildlife corridors? Where are the areas most vulnerable to sea level rise? Where is urban sprawl encroaching on farmland?
Answering complex spatial questions.
Exactly. It supports sustainable resource management, helps assess environmental impacts, optimizes infrastructure planning, and it's a powerful tool for public engagement using web maps to show people proposed plans or environmental risks in their area.
Analysis, planning, communication. It's central. Now back to data issues. What if an analyst finds conflicting information from two different data sets for the same area? Say, one map shows a forest, another shows new development.
Data discrepancies, another common headache. Again, methodical approach. First, identify the specific areas of conflict. Then investigate the sources. Check the metadata. When was each dataset created? What was the source scale or resolution? How was it collected?
Dig into the history of each dataset.
Right. Try to determine which source is likely more accurate or more current for the specific area of conflict. Maybe consult the data providers if possible.
Assess reliability.
Sometimes you might use GIS techniques like conflation, trying to intelligently merge the data sets, maybe taking the best bits from each based on your reliability assessment. Or you might have to make a judgment call and choose one source over the other for specific features, documenting why.
Merge or choose, but document the decision.
Exactly. Transparency about how discrepancies were resolved is crucial.
Okay. And remote sensing data, those satellite or aerial images, how are they actively used in GIS analysis? Can you give an example?
Sure. A common use is land cover classification. Say you want to map the different types of vegetation and land use across a large national park.
Okay.
You'd acquire recent satellite imagery, pre-process it to correct for atmospheric effects and geometric distortions, then use image analysis software, maybe IRDAS, Imagine, or tools within ArcGIS or QGIS to classify the pixels.
Grouping pixels based on their appearance.
Based on their spectral signature, yeah. Pixels representing dense forest look different from pixels representing grassland or water or bare rock. The software learns these signatures, supervised classification, or finds natural groupings, unsupervised.
Creating a land cover map from the image.
Right, a raster map.
Yeah.
Then you bring that classified raster into your main GIS project. Now you can calculate the area of each land cover type, see how it relates to park boundaries, rivers, trails, overlay other data.
Integrate it with other park data.
And you'd likely do ground truthing. Visit spots in the park to verify that the classification from the satellite image matches what's actually there. Helps assess the accuracy.
So image analysis creates a data layer that feeds into the broader GIS analysis.
Exactly. Remote sensing is a powerful data source for GIS.
Okay, final question. Before any analysis starts on a project, what are those absolutely critical checks an analyst does on the data to assess its quality and completeness? That initial vetting?
Right, that upfront assessment is vital. First, review the metadata thoroughly. Understand the data's lineage, purpose, scale, accuracy, update frequency, any known issues.
Read the label first.
Visual inspection in the GIS. Just look at it, zoom in, pan around. Do you see obvious gaps, weird spikes, features that look wrong?
Eyeball check.
Check for completeness. Are all the expected features there? Are there missing records in the attribute tables or required fields populated?
Make sure nothing's missing.
Verify accuracy where possible. Compare key features or attributes against a known, reliable source, like recent aerial photos or official records, or field checks, if feasible.
Cross-reference or ground truth.
Assess consistency. If using multiple data sets, do they align properly? Do attributes use the same codes or units? Are naming conventions consistent? Make sure different pieces fit together.
And use automated quality control tools available in the GIS software. They can often flag things like invalid geometry, e.g. polygons that cross themselves, duplicate features, or attribute values outside expected ranges.
Let the software help find errors.
It's a multi-pronged check to build confidence in the data before you invest time analyzing it. Foundation first.
Definitely sounds like laying a solid foundation. Well, this has been incredibly insightful, a real deep dive into GIS and the world of the GIS analyst.
It's a fascinating field.
For you, the learner, hopefully this painted a clear picture. GIS is this powerful way of seeing the world through location. Its applications are everywhere across so many fields. And being an analyst takes that mix of tech skills, analytical thinking, and communication.
Yeah, it's about understanding the where and using that to find answers.
So as you go about your day, maybe start noticing. Think about the location data your phone is generating, the sensors monitoring traffic or weather. How is all this spatial information shaping our world?
And how will GIS continue to evolve, especially as it merges more with things like AI and machine learning?
What new insights, what new capabilities are just around the corner? How will the role of the GIS analyst change? Definitely gives you something to think about.